Frankly, you know nothing about water. Unless you're a scientist, that was a bit arrogant. Hello and welcome to the beautiful individual that is watching this. I assume that after you read the title, you're probably wondering why I'm making a whole video out of plain old water. I mean, what's the big fuss? It's literally just water, right? Or so I thought too. I was so wrong. Surprisingly, there's a lot more to water than you think. Scientists are making countless new discoveries about water every day. We just might be scratching the surface of the mystifying properties of H2O. There's even controversy, yes, heated debates going on in the water world. Now, what we're getting ourselves into today is one of the most bamboozling, fascinating properties of water, which is ice. Before we get into the actual thing, I'm gonna give you a brief explanation about the phase diagram. So, what are the three phases of matter? Solid, liquid, and gas, right? Scientists use a chart called a phase diagram to visually map the phases which a matter exists in according to different temperatures and pressures. This right here is the phase diagram of water. As you all know, ice has a lower density than liquid water due to its hexagonal structure, and thus ice floats on top of water in your drink. So, if you take ice, fix the temperature, and apply high pressures to it and compress it, essentially decreasing the volume and increasing the density, it turns into liquid water. And if you take liquid water, decrease the pressure, and increase the temperature, it turns into vapor. And just like this, we know that by manipulating the conditions which a matter is under, we can deform and distort a matter's molecular arrangement. Now, what would happen if we further increased the pressure of liquid water, or decreased the temperature of ice to really, really low points? Would they forever stay in their original states? Or would they turn into something monstrous? Turns out, ice doesn't just stop, it's solid. Welcome to the real deal, my ladies and lads. If we expose ice to all kinds of temperatures and pressures, it can turn into all of these kinds of extraordinary shapes. And there are 20 types of ice, yes, 20, that we currently found to this day by doing that. Since we're talking about ice, let's zoom in the ice part. As we all know, this is the plain old hexagonal ice, known as Ice 1 or Ice 1H. It's the most common type of ice in the biosphere, but there's also cubic ice, or Ice 1C, which exists between 130 to 220 Kelvin, so it could be seen higher up in Earth's atmosphere. Now, let's put ice under really, really high pressures, and I'm talking megapascals and gigapascals. And now we get Ice 3, we move on to Ice 5, 6, and 7. These types of ice can be found in icy moons in our solar system, like Jupiter's Ganymede, where there's thick layers of ice up to thousands of kilometers thick. And interestingly, these can even be found on Earth. You can find Ice 6 and 7 inside of diamonds, deep in Earth's crust, under really high pressures. When ice changes form according to density like this, it's called a density-driven transition. Now that we've seen what happens when we compress ice, let's see what happens when we go the other way in the chart if we apply negative pressure to ice, essentially stretching the ice. What we can get are ice that are less dense than Ice 1, which are Ice 16 and 17, and these are called clathrate hydrates. And they are as fancy as their names are. Imagine a soccer ball that has gas inside of it. That's basically what a clathrate hydrate looks like, except the skin of the soccer ball is H2O, and there's non-polar gases or polar molecules that are hydrophobic but totally not homophobic in it. Clathrates are chemical cages that trap molecules inside of its structure. We call the cage structure the host molecule, and the gas or liquids trapped inside the guest molecule. Which kind of makes sense, right? It's like a host letting a guest in their house, except the house is a literal prison, and the host is basically strangling the guest. Clathrate hydrates are large ice cages that are formed around other molecules like hydrogen, oxygen, and methane. And without the support of these guest molecules, clathrate hydrates collapse into more conventional ice crystal structures, which is pretty cool, I think. Here is an actual photo of clathrate hydrate found on Earth, with the guest molecule being methane. Now, we can even go out of this graph, go to extreme conditions, not that it was not already pretty extreme. If we compressed Ice 7 up to 50 to 300 gigapascals and heated up to 2,500 Kelvin, you get Ice 18, and let me tell you, Ice 18 has really weird properties. It's also called superionic water. I'm going to tell you why later. And it's not even H2O anymore. It's kind of like both solid and liquid, and also like metal at the same time. In ice 18, water molecules break apart into oxygen and hydrogen ions. And while the oxygen ions crystallize into an evenly spaced structure, hydrogen ions just kind of float around the oxygen structure, behaving similarly to free electrons in metals. Well, believe it or not, mobility of hydrogen ions actually do make ice 18 as conductive as metals, making it a superionic conductor. Also, just like a metal, it can even be polarized when an electric field is applied. There's even ice that's not structured, which is called amorphous ice, whereas all the types of ice that we've previously looked at are crystalline, which all have defined long-range order. Now imagine liquid water molecules moving around having some nearby attractions, and you took a screenshot of it. It's basically what amorphous ice looks like. Amorphous ice forms when water has been cooled down so quickly that there just wasn't enough time for a stable structure to be formed. And because of its non-crystal structure, it's sometimes categorized as a glass. But it isn't entirely disordered either. It's somewhere between liquid and solid, where it's disordered in short distances but has order over long distances. This particular internal pattern is classified as a distorted hyperuniformity. One cool thing about amorphous ice is that it's used to estimate the age of icy moons and possibly the existence of extraterrestrial life. On icy planets or moons, the longer crystalline ice sits on the surface, the more it gets bombarded by ions. And that ion bombardment can turn crystalline ice into amorphous ice. So scientists can look at the ratio of crystalline to amorphous ice to estimate the age of that region of the planet or moon. The more crystalline to amorphous ice there is, the younger that region. And the existence of crystalline ice actually indicates a high temperature region and active geological activities. In 2021, a study used this to investigate Dione, one of Saturn's moons. And they found out that there may have been water under the icy crust in the past 100 million years. And liquid water means there is a possibility of life out there. Isn't something clicking here? Today, we've briefly gone through the 20 types of ice known to this day. So next time someone asks you, what are the 3 phases of water? You can now say, you obtuse nincompoop. What do you mean the 3 phases of water when there are over 23 phases of water hitherto discovered, including 20 types of ice? Just kidding, don't say that. Why? Because a recent study found the potential structures of 74,963 types of ice. And yes, this is real, it's stated in the Nature Journal. But to add to this Roman numeral system, you have to experimentally show the crystal structure. And scientists are waiting for the next person to do that for ice 21. Perhaps it could be you.